Hello everyone, and today's our Python tutorial will cover this how to solving shortest path problem using network and OR tools, and have some version update for this. As we introduce in our lectures, and the shortest path problem can be formulated as optimization problem, and also it is a network flow problems with a regular transshipment problem with the supply nodes. Okay, only one supply node and one demand node, and the supply node has a supply of 1, and the demand node has a demand of 1 as well. So we're trying to send 1 unit of flow through the network from source node 1 to destination node 5 with 1 unit, and see which way we can get the shortest distance to travel that. And this can be generated as a special case of a minimum cost network flow problem. However, solving this problem, we don't need to using the network simplex method, and we have plenty of combinatorial optimization algorithm can be used to solve problem like this. And in the first, we can using the so-called network simplex method to solve it, and NetworkX package. And today we're going to just using a show you several several algorithms available in the NetworkX package library. And also I have an update on the OR tools library as well. Okay, let's take a look at this example. Very simple. In the beginning, and we just import a NetworkX as NX and import the matplotlib pyplot, and set up some parameter for the visualization I'm going to use later on. And the next cell actually create a digraph, which is a directed graph, adding nodes 1, 2, 3, 4, 5, and node 1 has a demand of 1 and demand of -1, I'm sorry, and node 5 has a demand of +1. So the definition is a little bit different from our conventional network on the node demand and supply. They are only using demand right here for NetworkX. And also here I'm adding all the edges into the network. Okay, so I'm adding edges with the source node, destination node, and the associated weight. Like we did it before, we're going to plot the network as well using NetworkX draw edge label. So I'm posing the distance from each node pair on this graph as well. We did this many times. After we set up the network, solving shortest path problem using NetworkX is super simple. There are several different algorithms available. Of course, the first or most popular one is the Dijkstra algorithm. So we're just going to directly using the all pair Dijkstra path routine to solve for the shortest path. And I've stored this result in the dictionary form into a variable called path. Okay, the path, and then I can examine some of the element in there from node 1 to node 5. What is the shortest path? It's 1 to 2 to 5. It's 1 to 2 to 5. Okay, and also I can calculate so-called Dijkstra predecessor and distance both. Okay, and I give you a dictionary again. Okay, I give you the predecessor and the distance. So from node 1 to node 1 is no distance. From node 2, the predecessor is 1. Okay, predecessor is 1. And from node 3, the predecessor is 2. So actually, you see that from node 1 to node 3, distance is 8. From node 1 to node 2 and node 3, distance is 7. So it is the shortest path is coming from 2. For node 4, actually, node 4, the predecessor is 2. So 2 plus 4 equal to 6 is the shortest distance. From node 5, the shortest distance is 2. Also, is coming from node 1, node 2, and node 5. So it's presenting the solution in a slightly different way. Okay? And also, I can show you the distance. From node 1 to node 1, distance is 0. From node 2, from node 1 to node 2, actually, distance is 2. From node 1 to node 3, distance is 7. From node 1 to node 4, actually, distance is 6. From node 1 to node 5, distance is 14. It's 2 plus 12. So it's fairly simple, actually. And also, in NetworkX, we can call for the Bellman-Ford algorithm, as well as we introduce in our lectures, video, and handout. In that case, we can call all pairs Bellman-Ford path is similar to all pair Dijkstra path. So I give you a dictionary as well. For each node, what is the shortest path from node 1 to the source node all the way to the destination node. Okay. So fairly simple. So here is giving you the source node. It gives you a little bit. Remember, the Bellman-Ford is from every single source node. It gives you a list of a destination node and the corresponding shortest path. So, for example, node 1 to node 1 is from 1. Node 2 is actually going from 1 to 2. For node 3 is 1, 2, then 3. To node 4 is 1, 2, and 4. Okay, so I'll give you the shortest path. To node 5 is from 1 to 2 to 5. Look at another example. If the source node I change from node 1 to node 3, for node 3 to node 3, distance is 3 already. And for node 3 to node 4, actually is 3 to 4. From node 3 to node 5, actually go through 3, okay, to 4 to 5. So from node 3 to node 5 is actually from 3 to 4 to 5, actually total distance 16. And so on and so forth. Okay. And we do the similar thing is all pair shortest path to give you exactly the same result. So these two algorithms actually using the Bellman-Ford path algorithm. Finally, in our lecture, we mentioned another, we call the all pair shortest path algorithm, which means give you a matrix from any node on the network to any node on the graph. Okay, so we're using Floyd and Washer algorithm, and putting the graph I just defined it, and give you the result of from each one of the source node, what are the corresponding distance for each destination node. So this is for node 1, node 2, node 3, all the way to node 5. So this is a very simple, after you define the graph, solving shortest path programs using various algorithms is straightforward for NetworkX. Next, I want to mention a little bit update on the shortest path algorithm for all our tools. After version 9.4 update, the shortest path algorithm not yet available to the Python API. However, the C++ source is still available, and so in a future update, I just checked it yesterday, March 20th, they have an update updated to 9.6, and still the shortest path API is not available for Python yet, and the C++ library is still there. And so I will update you if I see any update with OR2 on this matter. And okay, so this is using a software package called NetworkX to solve for shortest path. As we mentioned in our lectures, we introduced in the last part of the shortest path algorithm. One is the Bellman-Ford algorithm we're talking about here, and the other one is the Floyd and Washer algorithm, and we illustrate it here. Actually, I would like to give you the two really quick tutorial for Bellman-Ford algorithm, and you can see that how these two algorithms, how easy it is to implement these algorithms. This algorithm is solving shortest path algorithm using the Bellman-Ford. This is a straightforward implementation without using any Python library. Okay. The example program, example I'm going to solve is look like this: 5 nodes, and there's some negative numbers on the arc. And this algorithm is fairly simple. If you look at this program is really short, and the majority, half of the program is printing out the result and detecting the negative circle if it exists. Okay, and rest of them are fairly simple. We define the class called graph and define the initialization of the graph. So we have vertices and edges. Okay, and define a simple subroutine called add edges. So allow user to adding edges to your network, to your graph. Then this is just printing out the result in the format version, and we can see that very simple printing routine. The Bellman-Ford algorithm is very simple. It's just determining if labeling which shortest path algorithm it is, the shortest path for each node. This is actually double for loop, I and U and V. Finally, this routine also detects if there is a so-called negative cycle exists. So here, fairly simple programs, no more than 10 lines. Most of them are comments and note. Okay, so here what we're trying to do is we're going to define this algorithm, then we're going to run through this example I had in the beginning. Okay, so here we easily solve this problem. Okay, only thing I wanted to make a note is here you see that from node 1 to node 4, from node 4 to node 3, and also from node 3 to node 1, there is a cycle exists right here, and the arc for 3 is -3, so -3 plus 1, and the distance is the cycle is 0. So I don't think we have a negative cycle exists right here in this particular program. What if the distance from 4 to 3, node 4 to node 3 is -4? What's going on? So we can actually quickly check out if that's the case. If I change this to 4 quickly, and the algorithm successfully detect there is a negative cycle exists, and that means there is no shortest path can be algorithm. We can circle this 143, 143, 143 multiple times and can get lower and lower negative distance. Okay, so just want you to pay attention to this, and this algorithm detects a negative circle as well for this case. All right. The next algorithm I would like to introduce in today's video is the Floyd and Washer algorithm in Python. And the example we're going to use for today's this notebook is fairly simple, 4 nodes, and okay, example. I will just want to show you how concise the Floyd Washer algorithm is. It's actually few lines, okay, and there's including 2 print, 3 print statement. So the algorithm itself is super concise and super easy. The only thing is you pay attention to this. There is a triple loop, okay? So as we illustrated in our example in our lectures, and there's a triple loop I and J for each one of the ij pair, and K is the intermediate node. So assuming K equals to 1, for example, from node 3 to node 4, okay, trying to see if I'm passing node 1, what is the distance? From node 2 to node 4 also. From node 2 to node 4 directly, I can have a distance is 4. But if K equals to 1, meaning I'm forcing the node 1 as an intermediate node. So the distance has to be calculated from node 2 to node 1, then node 4. So actually that distance is 7. So K is the intermediate nodes, and I and J is each pair of source and destination. And we can forming that so-called adjacent matrix for the distance. In this, I printed out each iteration and for each K, and as we introduced in our lecture video, for example, K equals to 0, which is 0 to 3, 0 to 4, and 0 means no 1, I'm sorry, here. And this is the program start with 0 to 3. So node 1, if the intermediate node is node 2, if the intermediate node is node 3, if the intermediate node is node 4, then we could have. And I also extended this a little bit with more explanation. First, I just want to show you how concise this algorithm can be, and then I add a little bit more description and the comment for you to follow. Same thing, the solving the problem is directly printing out each one of the so-called adjacent matrix throughout the update and at each iteration. The detail and the detail example, this example, exactly the same example, we did it by hand in our lecture video. So this is a very interesting algorithm, super powerful. Remember, the Bellman algorithm is you specify the Bellman 4 algorithm, you specify a source and give you the shortest distance to all the nodes on the graph starting from source node. However, the Floyd Washer algorithm is trying to calculate all pairs, any 2 pairs of source and destination node. What is the shortest distance between them? Okay, So a little bit different objective, and the complexity of the Floyd and Washer algorithm is the highest, but it gets more information in the solution. All right. So with this short video, we conclude several different ways to solve shortest path problems, either using the so-called NetworkX Python library, or using a straightforward implementation for both Bellman's Ford and the Floyd-Washer algorithm. All right, I'm going to conclude this lecture video. We'll see you in the next Python tutorial video. Bye-bye.